All right, so I think you guys know us, so I'll save the introduction here. So we're going to talk about X-ray photon correlation spectroscopy. So, not my slide. We're going to look at this length scale. This is a mesoscopic scale. So the Sands and Sachs group talked about this length scale here, but in their experiments they didn't have dynamic information. Some other groups have talked about this small length scale, atomic distances, inelastic scattering for the dynamics. But XPCS in particular is interesting because it covers a wide range of soft matter length and time scales, including colloids, micelles, polymers, and a lot of biological samples as well. So also not my slide. We have inelastic scattering down here, which is for very fast, very small things. We have dynamic light scattering using a different probe and other light source probes, which measure large and slow things. Well, actually, all sorts of time scales here. But XPCS is unique in the regime of relatively slow, relatively small. So that's what we're going to exploit today by looking at colloidal suspensions. So first, introduction to Sachs. We have X-rays hitting a sample, and we get a scattering pattern. I should have put Bragg's law in here, but I think you guys know it. So the intensity that you get from Sachs is related to mainly three different components. First is the contrast, which I don't know if you guys have seen this, but there's a map of which shows the contrast between air, water, calcium, and then some heavy metal. It's also related to S of Q. We're dying here. Sorry, guys. S of Q, which is the form factor coming from a single scatterer. So if you have a particle, it's coming from the shape there. And also the correlation between the scatterers, which is particle-particle relations. It's on I don't have long enough arms. So what we do in XPCS is we change this X-ray source to a coherent X-ray source. And what we get is speckled patterns. So if I still had the laser, I would point at the constructive interference and the destructive interference, but I'd probably miss anyway. So what XPCS does is it analyzes this speckled pattern as a function of time. So we have coherent X-rays now hitting our sample and making several patterns which we're collecting as a function of time. So we're looking at the time dependence of static properties in our system to understand the dynamics. So you can do two things. You can average over all frames and pretty much ignore the time component, and then you have just Sachs with really good statistics. You can also analyze it frame by frame to get spatial and temporal information combined. So that's what we did today. Thank you. So we're going to analyze this 2D pattern here, and we're going to look at a particular pixel as a function of time. And if you're kind enough to call me an artist, then this is an artist's rendition of the data. So we're looking at the intensity at a certain pixel as a function of time. And you'll see that it oscillates. But what we do is we calculate the autocorrelation function, which for the mathematicians are here. And this is what we get, a curve that goes down like this. So this is the detector, what it sees. What we can think about is a single scatterer shown here in some sphere. If we wait short times or look at large Q, then it will only move a little bit. It'll still be in there, right? But now if we watch for 8 seconds as it goes through like Brownian motion, eventually it'll leave the sphere. So this is essentially what we're saying. When we convert this to the intermediate structure factor here, you can read this as the probability of it still being in a certain Q sphere, sort of. So what's interesting about this is you now get the spatial information and the time information, which lets you look at the two as a function of each other and understand about the time scales associated with different length scales and the mechanism of diffusion. Here you go.
So our experiment was conducted at beamline 8 IDI at APS. For this experiment, we measured XPCS in the transmission Sachs geometry. So one of the things that was very important for XPCS is having spatial and temporal coherence of the beam. So we had a lot of X-ray optics and undulator that was important for that upstream. Then the X-rays, which were about energy 7.5 keV, scattered in transmission through our samples, which were a colloidal solution in capillaries. And the X-ray scattering, as Eric said, was on a detector downstream about 4 meters from the sample. The length scales that we can probe at sector 8 are from angstroms to microns, and the time range of the dynamics is from tens of nanoseconds to tens of seconds. And you can also do this in other geometries like wide angle scattering or in reflection if you have like solids or in plane structures. So the samples that we used were polystyrene spheres in glycerol. We wanted to study how the spheres behave in solution given the interactions between them. We have 2 samples. One is a 1.5% volume fraction. The other one was 34%, so we refer to them as dilute and concentrated. For the chemists in the room, this is glycerol and this is polystyrene. For the physicists in the room, we were measuring Brownian motion. And for the engineers in the room, we have a bunch of balls that are hitting each other. So as so as Eric showed, this is the pattern of scattering we get. We can average over concentric circles in our pattern to get functions of intensity versus 2 theta, and you can use Bragg's law to get intensity versus Q. So this is a model of Sachs data from perfect spheres with a spherical form factor. If you remember during the talks when we talked about Sachs data, these sharp oscillations are because it's perfect spheres. So since we're measuring spheres in solution, we should expect to see some oscillations. And this is our data, time averaged Sachs data. And yeah, we see oscillations. They're not as sharp because we don't have perfect spheres. But the main difference between the dilute and the concentrated samples is right here, this peak. This is due to the correlations of the spheres in the more concentrated samples. As the Sands group pointed out, the intensity goes as the form factor times the structure factor. For the dilute solution, where the for the dilute solution, there are very few interactions, and so the structure factor is essentially 1. But for the concentrated sample, it's not. We can actually divide the intensity from the concentration sample by the dilute sample and get the structure factor for the concentrated sample. This peak right here is at about 0.0045 angstroms, inverse angstroms in Q. That corresponds to about 140 nanometers and tells us it's a measure of the sphere separation in the concentrated solution.
So once we have the static structure factor, we go to the dynamic part of it. So these are basically plots of the correlation function that we determined using the intensities at the same Q at different times. So these are different times, and at each Q, which is basically each pixel on the detector, you can get plots, and they do it for the number of pixels that they have. Each of these plots can be fit easily to an exponential with one parameter, which is just the time constant at that Q. So you would expect that as the Q increases, which is basically going towards smaller distances, it takes lesser time to relax, so the time constant should go down, which is what you see. So once you get the autocorrelation function, so you get tau as a function of Q. So this can be plotted. So this is basically tau as a function of, so here I changed the axis to inverse of Q squared. So this is basically length at this point. And so this is the dilute solution, this is the concentrated solution. So getting back to normal diffusion, so diffusion is r squared by t, r squared obviously is proportional to wave vector inverse by tau. So the slope of these curves represent 1 over diffusivity. So as you can see, the dilute solution follows Brownian motion with a single diffusion constant, whereas the concentrated solution basically has 2 diffusion constants per se. So one is the short distance motion and the other is the long distance motion. So when you have really concentrated solutions, you can assume that each particle is in a cage of other particles. So short distance motion basically implies rattling of a particle within the cage, which is one diffusion constant. And the long is basically escaping the cage and then going to out of the cage. So that is the long distance motion. So again, this is Q inverse, so that's why this is actually R. So this is increasing R here. So why does this happen? Why do we have two different diffusive coefficients? So that happens because, so as Sheena mentioned, we got Brownian motion in dilute particles. So these are basically friends, rather acquaintances who meet once in a while and go ahead. Hydrodynamic interactions are good friends. When they go down, they take everybody else down. So that's why you have, when these particles move, the solvent moves with them. And that solvent basically puts a force on, on every other particle in the vicinity, which basically impedes its motion, therefore leading to a lower diffusion coefficient. So these hydrodynamic interactions don't start playing a part until higher concentrations, which in our case we saw at 34% loading. We do see hydrodynamic interactions which basically lead to different diffusion coefficients. One of the most important results from this is basically, so this is the structure factor that Sheena showed. So the blue curve is the ratio of the the Brownian diffusion coefficient to the diffusion coefficient to the short length diffusion coefficient. So as you can see, very close. So this is basically Q again. So I'll go from here to here. So this is basically small distances. So when you have small enough distances, so you're basically looking at a particle and very near it. So that's as good as Brownian motion. So that's near 1. As you get closer to the end of the cage, you basically have a large impedance to your movement, which basically leads to this considerable drop in diffusivity, which again decreases, the diffusivity again increases at long time scales because now you're basically moving in the bulk. So in conclusion, we saw that XPCS works on 6 orders of length scales and these time scales and these length scales. And with our system, we saw that there's a minima corresponding to diffusivity corresponding to the maximum in the structure factor. We would like to thank Argonne, DOE, Oak Ridge, and all of you for good company, and everyone at Sector 8 for helping us out with the data analysis. Thank you.
Some questions?
You had a more complicated, so essentially, we did the XPCS too, and you pretty much get those 2 lines, and then you make a lot of extrapolations from the slopes. You had like a more complex sample. Could you really tell what's going on?
So that would then depend on the number of time scales and how well resolved they are in Q. So I don't actually do XPCS, so I'm not sure if there is literature out there. But then, if it's spatially resolved enough, I'm sure you can differentiate different time scales. Yes.
So these curves here you can fit with any function. We chose, as he said, this one on the left, which is like the easiest one you can find. So more complicated systems make this fit worse and worse. So if you know what you're looking for, or this is something you can simulate in molecular dynamics and things like that. So there are ways to figure out how to interpret this, but this is where you would see the complications. It's just a matter of, can you make sense of them?
And I know there have been experiments like Andre gave the example of antiferromagnetic fluctuations in domains in chromium. That's way more complicated. I don't know the specifics of it, but yeah, it's not spherical particles, obviously. That's
Can we somehow measure the hydrodynamic interaction?
So that's, yes, you can. So the diffusivity, basically, I did not show the relation here. So diffusivity basically scales that diffusivity is equal to Brownian diffusivity, H of Q by S of Q. H of Q is the hydrodynamic interaction structure factor by S of Q. So we basically divide so this plot is actually a measure of hydrodynamic diffusivity, this one, by structure factor. So we need to divide the structure factor out of this. And then, as you'll realize, if we divide the structure factor out of this, you'll basically get a proportional constant, which means that hydrodynamic interactions in concentrated solutions are prevalent through all length scales.
How do you determine the form factor for a more complicated shape other than a sphere?
somebody presenting SACS?
I can write down the, so
Okay.
you-
Then we'll do it. The way that we did it in SACS was our group also did SACS measurements as well. You measure a dilute solution, and then you just run a sort of biased Monte Carlo to generate different shapes. This is if you have a monodisperse solution. And then you just keep iterating over that. And the other option is to do the exact opposite and build your structure, and then you can calculate and then Fourier transform exactly what X-ray scattering is measuring. So you can go at it either way. But that's what's hard to do if you have non-spherical or dispersed particles.